So it's a great pleasure to introduce Brendan Murphy from the University of Bristol, who's going to talk to us about approximate subgroups of soluble linear groups over finite fields.
Great. Thanks, Sean, and thanks for having me here. So I'm going to speak about a result in growth in groups, and before I get into that subject, I'll just sort of discuss what the words in the title mean. So we'll begin with approximate groups. So approximate groups are relaxations of finite groups. So a finite subset of a group is a k-approximate group if it contains the identity, if it contains inverses, and it satisfies this relaxed version of the closure property. So instead of every product living in the set A, so this set A squares, the set of all pairwise products of elements of A, that set of pairwise products is covered by k left translates of the set A. And so if k equals 1, then a k-approximate group is an actual finite subgroup. And so it's a relaxation of this concept. And I'm just going to list a few properties of approximate groups. But the main idea is that they behave like finite subgroups, but there's this parameter k, and as you do various operations, k gets a bit worse, but in a reasonable way. So first, this covering property implies that if you take iterated products of your set A, then the size of that set of iterated products doesn't grow too quickly. So if you iterate this covering property, then the set of products of k elements of A is contained in this product set, so we need more left translates, but the number of left translates is now k to the little k minus 1, and so we have this reasonable bound on the size of the set of k-fold products. And conversely, if we have a finite subset of a group, and we know that if we take threefold products, so this is the set of products of 3 elements of A, and that set isn't much larger than the original set, then we can form an approximate group by making sure that we have the identity, inverses, and then if you square this set where you've thrown in inverses and identity, then that gives you an approximate group with a bit of loss in this parameter k. So roughly equivalent to the property of being an approximate group is being a finite subset of a group that satisfies small tripling. And sometimes one property is easier to work with. So some important properties, you take a homomorphic image of a k-approximate group, and that image is also a k-approximate group. So that's sort of obeying the philosophy that approximate groups act like groups. And essentially, the same thing is true. If you were to intersect two subgroups, you get a group. If you intersect an approximate group with a subgroup, you get another approximate group, more or less. You may have some losses in k, but the idea is that any operation you could do with a finite subgroup, you can do it with a k-approximate group, and you should get back a k-approximate group, perhaps with a slightly worse value of k, roughly speaking. Okay, so approximate groups are sort of finite groups with a parameter, a sort of a fuzziness parameter. Okay, so some examples. The simplest example probably is a sort of a centered arithmetic progression. So if we just take the integers from some negative n up to positive n, then if we sum the set with itself, then we get integers from minus 2n to 2n, and so we can cover the sum set by 2 translates. We just shift to the left by n, and we shift to the right by n. And generalizations of this include basically homomorphic images of a box in z to the d, or z to the d intersected with a convex body. So So those are sort of familiar examples from additive combinatorics. Other examples that make sense in the Abelian and non-Abelian world are finite subgroups. So one approximate group is a finite subgroup. If you pass to a large subset of a finite subgroup, you preserve small tripling, so you can use one of the properties from before to get an approximate group. And you can also add a small number of elements that commute with your approximate group, or commute with the group is contained in. So those are some familiar examples, and a slightly different example is a sort of a nilpotent analog of an arithmetic progression. So if you look at the group of 3x3 matrices, upper triangular matrices with ones on the diagonal, that's a nilpotent group. Say we'll take entries in the reals, and the set A here, you can verify pretty easily that it has small tripling. And so it wouldn't be hard to make an approximate group from it. And so this is sort of an example that's essentially different from the previous two. It's sort of like a non-Abelian analog of a progression. Okay, and so the definition of an approximate group has this sort of combinatorial covering condition, and examples of approximate groups are sort of algebraic in nature. So subgroups are algebraic in nature, and then these progressions and nil progressions are sort of like maybe a bit like taking an initial segment in some cyclic group in the first case. Okay, so we have these nice structured examples, and sort of the goal of studying approximate groups is to try to characterize an arbitrary approximate group in terms of these examples, or some finite list of examples. Okay, so there's some results in additive combinatorics where we're maybe I'll step back. So sort of combining results of Freiman, Green, and Ruja, if you have an approximate group in an abelian group, then it is true that that approximate group is essentially controlled by some combination of generalized progressions and finite subgroups. Right, okay, and so let's look at sort of a non-abelian version. So Helfgott proved a product theorem, or a growth in group theorem for SL2 over the prime field FP, which says that if you have a generating set, then either that set, when you take a threefold product, equals the whole group, or the set of threefold products is significantly larger than the original set. So you either have growth, or if you don't have growth, that's because you've filled out the whole group. And if you take a contrapositive, you can rephrase this as a structure theorem for approximate groups. So if A is a K approximate group, which is basically saying that this growth condition doesn't hold for some choice of K, then either A doesn't generate, so it's contained in a proper subgroup, or A is quite large, which you can get out of this first condition. So this is quite a bit different from Freiman's theorem. And so this is sort of the sort of result that you might prove in a non-abelian setting. So, okay, so we'll come back to structure theorems for approximate groups, but before we do, I just want to give some definitions so that we can be a bit more precise about the results we describe. So first we'll be looking at linear groups, which are subgroups of the general linear group over a field. I guess classically you would think of the field as being the complex numbers, and then you would look at closed subgroups. For this talk, F will be typically a finite field, or maybe the complex numbers. And so the sort of groups that we were interested in. So the classical groups, one of them came up in Herold's theorem. So the special linear group, the special orthogonal group, which preserves a symmetric positive definite form, or the symplectic group that preserves a alternating form. So these are all subgroups of some GLN, and over the complex numbers, they're closed. Two subgroups that are particularly important for this talk are the upper triangular group and the upper triangular unipotent group, which is the subgroup of the upper triangular group with ones on the diagonal. Okay, so those are some linear groups. And so nilpotent and soluble groups will also be coming up. So these are groups that are built from abelian groups in sort of a nice way. So a soluble group has a terminating derived series. So the derived series is the series of subgroups you get by just repeatedly taking commutators of the previous term in the series. So you have a group G, you take its commutator subgroup, then you take the commutator subgroup of the commutator subgroup, and so on. And if that series terminates, then your group is soluble. A more restrictive condition is that your lower central series terminates. So in that case, your group is nilpotent. And so the lower central series is formed by taking sort of one more commutator with the previous level. So you start with G and you take a commutator with G, and then you take the commutator's subgroup of G and the previous term, and so on. So the quotients at each level are abelian, and the central series has a slightly nicer property that we won't actually discuss in detail here. Okay, so two examples are the subgroups I mentioned before. So the upper triangular group is soluble. If you take its commutator subgroup, then you end up in the unipotent subgroup. And the rest of the derived series then sort of is majorized more or less by the lower central series of the unipotent. So once you take the commutator subgroup of this, will be in the first term of the lower central series of the unipotent subgroup. Okay, so we'll just look at the lower central series of the unipotent now, and we'll see that that terminates, and so that would show us that the upper triangular group is soluble. So here's the lower central series of the 4x4 unipotent subgroup. Each time you pass to the next term of the lower central series, you kill off a diagonal here. So in the first step, the commutator subgroup kills off this first off diagonal. And then if you take commutators with U4 again, you kill off this next one, and then you kill off the last row. Okay, so and this is sort of maybe the most important example of a nilpotent group, or it's sort of where the term comes from. Okay, so now with those concepts, we'll describe some structure theorems for approximate groups in a bit more detail. Okay, so first, Helfgott's result on SL2 generalizes to all finite classical groups and actually a slightly wider array of groups. So this result was announced the same day on arXiv by Briard, Green, and Tao, and separately by Pieper and Szabo. So if you have a finite field, not necessarily FP, just any finite field, and you have a almost simple algebraic group, which includes the examples that we gave before of the classical groups, and you have a k-approximate subgroup of that group that generates, then either the set your k-approximate group is very large, or it's very small. So these are sort of two trivial ways to have k-approximate groups, and those are the only possibilities if you have a generating set. And so with this result in hand, there's sort of an enticing strategy to generalize and classify any approximate subgroup of GLN. And so the idea is from the theory of linear algebraic groups, if you have a closed connected subgroup of GLN, then you can decompose that subgroup as essentially a product of simple groups, or a semi-simple piece and a soluble radical. So the idea would be, now that we know how simple approximate groups work, if we could classify soluble approximate groups, then we are on the way to proving a sort of a structure result for all linear approximate groups. This was the transition to proving a result for all approximate subgroups of GLN from this decomposition. It's not straightforward, but it's sort of the first step. If you can classify simple groups and soluble groups, maybe you can classify all approximate subgroups of GLN. Okay, and so some progress was made on this by Gill and Helfgott, who proved that if you have a k approximate subgroup of GLN over Fp, the field with p elements, p is a prime, and A generates a soluble group, then you have the following structure. So A is covered in a small number of translates of a soluble group. So these translates you can sort of think of as a bit of noise. A small number of products of A contains a unipotent group, which just means a subgroup of the full unipotent group, so that the quotient of S by U is nilpotent. And this is sort of qualitatively the best you can hope for, because as we saw with the nil progression, you can have a subset of a nilpotent group that grows very slowly. And so actually Gill and Helfgott combined the result with the result of Matthew Toynton to get even more precise structure. So you can say actually that this nilpotent part looks like a nil progression by a finite group in some sense. Okay, so Gill and Helfgott reduced the case of soluble approximate groups to essentially proving structure for nilpotent approximate groups, and that's been done. But the result only works over Fp, so it still leaves open the question of what happens to soluble approximate groups over Fq, and then there's the question of putting this together with what we know about simple approximate groups to prove the structure result for all k approximate subgroups of GLN. Okay, so there's a conjecture by Helfgott and Lindenstrauss, sort of informally, which suggests what the structure of a general approximate subgroup of GLN over any finite field should be. So first, you have to account for a bit of noise. So there might be some translates that don't cause a lot of growth. Right, so you could remove a bit of noise, and then after you do that, there should be some subgroup that you can generate very quickly, so that the quotient of sort of this denoised group by the subgroup you generate is nilpotent. And then, so essentially a k approximate group should be finite by nilpotent. So I think the motivation for this result maybe comes in two different ways. So Helfgott, when he extended his SL2 theorem to SL3, he kind of noticed that if you take the contrapositive, the structure you get is that a k approximate group is either very large or it's not a generating set. So it's contained in some subgroup, but that's not incredibly specific. So he went further and proved more. So he described, well, refined the alternative that you're contained in a subgroup. And so this conjecture is more or less the generalization of that work from his paper on SL3. And Elon Lindenstrauss, I guess, probably communicated via Tao's blog, suggested that the structure theorem for a general approximate group should look something like Gromov's theorem from geometric group theory, which says that if you have a finitely generated infinite group, and the size of the balls corresponding to some generating set, if the size of those balls grows polynomially, then that group is finite. Well, it's virtually nilpotent, which is a bit like finite by nilpotent. And so this is the finite analog of that statement. So what is actually known? Gill and Helfgott prove this conjecture when Q is a prime, combining with some result of Peter and Szabo. Actually, Briard, Green, and Tao in a separate paper proved a more general result. So actually, they don't restrict to linear groups, and they prove a similar structure theorem, except in the first point, the number of left translates taken to cover this group gamma is not specified, so it's not polynomial. And in fact, John Eberhardt proved that this kind of dependence in the most general case is impossible. So a very general version of this is known, that's quantitatively not as good. If you replace FQ by the complex numbers, then Briard, Green, and Tao prove this result, basically combining the result on almost simple groups with some previous results of Briard and Green. So, so what's left open then is to prove the Helfgott-Lindenstrauss conjecture when Q is not a prime. And so the first step towards doing that would be to extend Gill and Helfgott's theorem to the case of a general finite field. And so, so in unpublished work that hopefully will be up soon, I do just that. So, right. So the main result that I want to talk about then is the extension of Gill and Helfgott's theorem to all finite fields. Okay, so we'll look back and see what Gill and Helfgott did, because actually the strategy I use is broadly the same as theirs. The main differences are technical in some sense. So we'll look back. Their strategy is pretty natural. So okay, so this is the setup. We have a subset of the general linear group over Fp, and it generates a soluble group. We can assume that the group it generates is upper triangular, either by passing to an extension or sort of increasing the dimension here, but let's just assume that A generates some subgroup of the upper triangular group. And so therefore the group it generates is soluble. Okay, and remember we want to find a subgroup S that covers A with a few translates, and then we need a subgroup U that we can generate quickly so that the quotient is nilpotent. And basically there's some pigeonholing you do at the beginning to remove the noise. And so we'll take S to be equal to G. So S is this soluble group that nicely covers A. In this case, we'll just assume that it's the group generated by A. And so our main goal is to find a unipotent subgroup so this quotient is nilpotent. And so what we do is we make the sort of, well, we don't make a choice. We take the easiest, the thing that has to work, which is the last term of the lower central series of S. So S is not necessarily nilpotent, so it doesn't terminate, this lower central series doesn't necessarily terminate at the identity. If it did, we were done, so that's good. If not, the lower central series terminates at some subgroup because S is a finite group, so the sequence has to terminate at some point. And the last term will be unipotent because once we take commutators, this commutator subgroup is contained in the unipotent group. Okay, so this is a unipotent group, and if we quotient, then because commutators commute essentially with holomorphisms, if we can just quotient this whole series by u, we'll see that the lower central series of S modulo u terminates at the identity. So we get a nilpotent quotient. And actually, any nilpotent quotient would have to factor through this one. So this is sort of the easiest choice, I guess, to generate. Okay. Right. So what's left to do is to generate this subgroup U. Okay. And so one of the main ingredients that goes into Helfgott's theorem is a sort of a generalization of the sum product theorem. Or maybe I guess you could see it as putting the sum product theorem in the right context. So the sort of result that we'd want to that they generalize is the following: if you have two subsets of Fp and the elements of B are invertible, then if you form this combination sum and product, the size of the set, well, this set must grow unless it's quite large. So if A and B are both close to size P, then we won't get much growth. Otherwise, we usually get some amount of growth depending on the size of the set of scalars. And so the group action version of this, you should think of the multiplicative group of Fp acting on Fp by multiplication. So the multiplicative group is replaced by just some abelian group acting on another group. And we'll write this by exponentiation. Okay, and so now if we have a subset of the group gamma that's acting and a subset X of the group that's being acted upon, what we'd like to do is combine the group law in H, which corresponds to addition, with the action of gamma, which corresponds to multiplication. And sort of the philosophy is that if we combine these two separate actions, then we should get some growth unless there's some natural obstruction. So that's what happens. There's just a bit of a technical point that you have to deal with. So we have the subset A of the group that's acting, and we have to look at the set of elements that it fixes besides the identity. So that set is slightly problematic. So right, but Helfgott's group action sum product theorem then says if we take sort of this product set, we take A inverse times A, and we apply that to our set X, and then we take 6 products of that set. So essentially, roughly, you could think of that as of summing maybe 6 copies of something like BA. Then that should grow, provided that this fixed point set isn't too large. So as long as this fixed point set is significantly smaller than the size of A, then we get some growth. Otherwise, we can generate an A invariant subgroup that contains X in H. And so this is a thing that can't grow. This is A invariant subgroup, and it's generated quickly. So this is sort of the group action version of the sum product theorem. It says if you combined a group action with a group law, then you should get some growth unless you're very close to generating an object that can't grow. Okay, and so now the connection of this problem of proving growth in soluble groups, or the upper triangular group, with the sum product theorem is not too hard to see, especially in the 2x2 case. So if we conjugate an element of the unipotent group by, say, a diagonal matrix, then we multiply by another element in the unipotent group, well, we get back a unipotent matrix, and what's happened is we've multiplied one term and then we've added another. So we have this sort of combination sum and product. And so the idea is if we can set it up to apply the sum product theorem in this sort of upper right hand corner, then we should get some growth unless essentially these x's and y's occupy almost every possible value for this upper right hand corner. And for higher dimensions, the action looks somewhat similar. So if you have a true diagonal matrix, then sort of you get multiplication by ratios of the terms on the diagonal. And the product in the group is, at least on the first off diagonal, just addition. And then as you move away from the diagonal, you incorporate some more complicated terms. Anyways. Okay, so let's look at the 2x2 case to see how sort of the sum product theorem comes into play and how that corresponds to the statement of Gill and Helfgott's theorem. So, okay, so we saw that if you conjugate by a matrix with diagonal terms a and b, then that multiplies a unipotent element by this ratio. So we'll look at the set of ratios that come from elements in A, and then we'll also look at a set of unipotent elements in this fourfold product. The idea of taking this fourfold product is that it will contain all the commutators of elements in the set A. Anyway, so we get some ratios and we get some unipotent elements, and then if we conjugate a to the 4 by a, that's contained in a to the 6, and then if we multiply again by this a to the 4, then within 10 products of A and in the unipotent subgroup, in the upper right hand corner, we have this combination sum product set. On the other hand, because if A is an approximate group, then the number of products here doesn't actually change the size of the set too much. So this is set here with a to the 10 is not much larger than you would get if you had a to the 4. And so we have that this combination of sums and products doesn't grow very much. And so combined with the sum product theorem, or remember this term on the left is at least some constant times p, or it's size of c times b to some delta. If we substitute that in and solve, we have either that this set of unipotent elements is very large. Remember, if we're over fp, then there's at most p values for this term x. So this would be saying that we're very close to full unipotent subgroup. Or there's very few ratios that would come if b is small. And so right, so if we're close to having all of the unipotent elements, that this first conclusion basically says that if we take a few more products, we'll be able to get the whole unipotent subgroup. So in that case, we'll let S be the group generated by G, and we'll let U be the group generated by this fourfold product. And if you take the quotient S modulo U, then the quotient will be abelian because there's actually all of the commutators of the generating set of S that are contained in the kernel of that map. Okay, so if we have the other conclusion where there's few ratios, then we actually want to do, this is where the refinement step comes from. So if there's few ratios here, then the sum product theorem doesn't really have enough power. So instead we pigeonhole to make this ratio constant. And then that actually puts you in an abelian subgroup. So you just take S to be the subgroup generated by that set you pigeonhole to, and then you'll let the unipotent group be trivial. Okay, so in the 2x2 case, it's just an application of the sum product theorem, and it just takes a little bit of fiddling to set up. And so the refinement step that I alluded to in the general setup basically comes from when you have very few ratios, you sort of then the cosets corresponding to those ratios are just noise, and you should throw them out. Okay, so right. Okay, so the idea, I guess, then to go to higher dimensions would be you have sort of a diagonal subgroup, and you could act on the unipotent subgroup, and you would hope to apply this group action product theorem. For instance, right, if you were to just look at this first off diagonal, then you would have the exact same situation. You'd be multiplying by these ratios, and you'd also be getting sums from the group product. So you could try to use the Gill and Helfgott theorem in a similar way. There's some technicalities, I guess. You need to be able to describe the set that you're acting on for a number of reasons. And in particular, this set of fixed points can be problematic. So you need to guarantee that there aren't any points that are fixed, say, by everything in your group gamma. So so the philosophy is somewhat similar. You want to use the diagonal group acting on the unipotent group and apply a sum product theorem, but it takes a bit more work to set it up and make sure that all the conditions are satisfied. And so to do this, Gill and Helfgott prove a very nice structure theorem for unipotent subgroups over FP. It says, so the idea behind this is roughly the following. So if you look at the full unipotent subgroup over FP, its Lie algebra consists of upper triangular matrices with zeros on the diagonal, and those are nilpotent matrices. And since if you take powers of nilpotent matrices, eventually they go to zero, you can define the exponential of the nilpotent matrix, and there's a nice exponential log correspondence between this unipotent group over FP and its Lie algebra. And so if you have sort of an arbitrary unipotent subgroup, Gill and Helfgott show that that unipotent subgroup is the product of all one-parameter groups that are contained within it. And these one-parameter groups, they come from exponentiating a single element in the Lie algebra. And so, again, this is a polynomial map because this series terminates after like n terms. So more or less, they can show that any unipotent subgroup of the full unipotent subgroup over FP is an algebraic set, and this lets them use the theory of linear algebraic groups to characterize sort of the group generated by a soluble approximate group, and it also is a nice way to sort of to work with the unipotent subgroup. In the 2x2 case, there's kind of only one variable, so it's easy to do by hand, but things get trickier once you move into higher dimensions. And so this is sort of a key part of their argument is this Lie algebra correspondence. And then they use that in combination with their group action product theorem. Okay, so this Lie algebra correspondence doesn't really work if you go to extension fields of FP. So if you look at this one parameter group, where T is ranging over degree 2 extension of FP, you take the derivative and you look at the this one parameter group goes to the origin. So if you look at its derivative there, you get this matrix. And if you exponentiate this matrix, you end up with a different one parameter group. So it's not true in general that essentially that taking the logarithm of a matrix and looking at a Lie algebra are the same over extensions of FP. So okay, so basically all the structure theory that Gill and Helfgott prove has to be redone somehow. So that's sort of one problem with generalizing their arguments. And sort of another problem that comes up in various places is that the subgroup chains of the unipotent group over FP have a bounded length. really the most, well, n squared is a generous estimate for the length of a chain of subgroups of un over fp, but if you have extensions of fp, then you can have arbitrarily long chains, and so this is problematic for various parts of the argument. Right, so this is sort of like the two main issues to deal with. So I'll explain how, I won't explain directly how you overcome the second issue, or where it comes up, but we'll look at sort of how the argument in higher dimensions goes, and where you need some new input. Right. Okay. So, all right. So here's a bit of a sketch. So here's an example that illustrates a few interesting features. So, so let Q just be p squared. So we'll take sort of the smallest extension we can, and we'll take a subgroup of the upper triangular group over FQ. And we'll suppose that A generates a group that looks like this. So the elements on the diagonal are in FP as a subfield, as are the elements in the first off diagonal. But then in the top right corner, we'll take elements in the full extension field. Okay, and we've also, we don't have freely varying terms on the diagonal. So, so remember in the 2 by 2 case, so the ratio of A to B came up, and actually sort of there's some important homomorphisms from G, which are the ratios of various terms on the diagonal. And so if you had so the most general possibility would be that you have sort of 3 non-trivial characters that are giving you ratios of the diagonal. In this case, there's only, well, there's a trivial character giving you the ratio of these outermost diagonal terms. And then these 2 characters corresponding to the ratios of the first and second, and the second and third are reciprocal. Okay, so there's this group is not sort of completely general. Okay, and the group that we want to generate is the last term of the lower central series. In this case, you get it in with taking 3 full commutators. Okay, so we'll take a closer look. If we take the commutator subgroup, right, we just kill off everything on the main diagonal. When we pass to the last term of the lower central series, we actually change what happens in this upper right-hand corner. Okay, so okay, and so it'll turn out that we can generate this group quickly. This group is unipotent, and if we take the quotient of G by this group, we get something abelian, so certainly nilpotent, but this group we won't be able to generate. And we'll sort of see why that's the case. Okay, so we want to apply the Gill and Helfgott group action product theorem, and there's this condition about elements with non-trivial fixed points that we need to take care of. Okay, so it turns out that this is Gill and Helfgott's strategy, and it's the strategy that I use as well, is that what you want to do is you want to generate U sort of level by level. So instead of generating all of U at once, we'll generate each factor of its lower central series. So we're going to look at the lower central series of U, and U is the lower central series, last term of the lower central series of G. So we're using the lower central series sort of in 2 places. Right, and so what happens if we quotient out by the derived group of U is that we just basically know what's happening in this upper right-hand corner. And so now we can look at what conjugation by any element looks like. And I've just put stars here because no matter what terms you put here, it doesn't affect the output as long as you're ignoring this upper right-hand corner. And what you get is that or this quotient group is an abelian group that corresponds to this off diagonal, and conjugation just multiplies by these ratios, and you can see that there's no non-trivial fixed points. So that means the product theorem is going to work nicely. Okay, so this then, in this particular case, everything goes like the 2 by 2 case. Just using a sum product theorem, we can generate the subgroup U modulo its derived group by some bounded number of products of A. And so what that says essentially, you'll get some result like this, that in the 2 by 2 case, we started with, say, a to the 4, and then we went to a to the 10. And that generated all of the unipotent group. In the 3 by 3 case, now we've only generated modulo the derived group. So we get something like this. And then you could actually say something a little bit more useful, but this is the idea. And so what's left to do is generate the derived subgroup of U quickly, and then we'll be done. Okay, so the problem here, which I've covered up, so I have to go back. So the problem then for generating the derived subgroup is if A equals C here, when we conjugate, then the action in this upper right-hand corner is trivial. So there's no product. There's only sort of the sum bit of the group action product theorem. Okay, so right, so we need to deal with this. We can't use the sum product theorem. So what we can say, if we have a subset that generates U modulo its derived group, and there's a theorem of Burnside called the Burnside basis theorem that says if you have a subset that generates modulo, modulo the Fertini subgroup, which is sometimes the derived subgroup, let's just assume they're equal for now. So essentially, there's a theorem of Burnside that says if you generate modulo the derived group, then you generate. So this finite number of products we found is a generating set for U. So we should be able to get the commutator subgroup. It just, then the question is how quickly can we generate it? Okay, and so there's another idea. It's shows up in Matthew Turning's work on nilpotent groups and in Gill and Helfgott's work. Sort of a more explicit way of saying that if you generate modulo the commutator group, then you generate the whole group. You can actually describe the remaining levels of the group in terms of commutators modulo the derived group. Okay, so I've put stars here just because well, whatever is there won't matter in this computation, and this bracket is group commutator. Okay, and so you could think of these matrices as elements of this abelianization, and when you take their commutator, you get an element in the derived group, and that depends only on the element in the abelianization. So essentially, we have this abelian group, the abelianization, and there's a bilinear map from it to the derived group. And so the derived group by definition is generated by commutators. So if we put it through this bilinear map, then the derived group is generated by matrices of this form. And these variables only depend on however many products it took us, how many products of A it took us to generate this quotient. Right. So here, I guess the example I gave maybe becomes a bit boring because actually we only wanted to generate FP here, and if you have at least P elements here, you'll get that. So let's see. Okay. Anyway, so the thing that happens in general then, if this derived group is fixed, then you have to generate using this bilinear map. So this is sort of where you'll end up. Okay, so we have a subset of the upper triangular group generating G, and U is the last from its lower central series. And suppose if we take enough products of A, I guess this should be intersected with U. then it generates modulo the commutator subgroup and gx trivially on the commutator subgroup. So that's sort of where we were. So right. So the image of this product of A in the abelianization under the commutator map is contained in some bounded number of products of A intersected with a commutator subgroup. So if there were 20 products here, then commutator involves 4 products, so that we could take this constant to be 4 times whatever we had here. And the image of this abelianization under the commutator map generates this, by definition, the set of generators of this commutator subgroup. So we found some finite number of products that generates the next term of the of U, of the lower central series of U. Right, but so some number of products of this set, so some number of products of A intersected with the derived subgroup will contain all of the derived subgroup. And so what we need to do is show that it generates quickly. So this is sort of the general setup. We have this abelianization and we have a bilinear map to the derived subgroup. And so the image of V cross V under this bilinear map is contained in some bounded number of products of A. But remember that A is an approximate group, and this derived group is a finite subgroup. So this intersection is an approximate group. And if we take products, the rate of growth is quite slow. So this is sort of the general problem. You have a subset of an abelian group. It contains the image of this bilinear map, and it grows slowly. And so you can prove using some Fourier analysis that the only way that can happen is if this set is extremely large to begin with, almost as large as possible. I didn't write out the details of the theorem because it's a bit long-winded, but so basically the image of this bilinear map just has to be very large if it doesn't grow. And so the hypotheses that we have say that it doesn't grow, and so so we can generate this last bit of the group U that we couldn't generate with the sum product theorem, just using this commutator map. Right. So I guess the thing is that a priori it's not clear that the image is very large, but it has to be if it doesn't grow. So there's a bit hiding here. This actually, to force this to happen, you need to do the initial refining step correctly. So there's some stuff hidden here, but basically if you do the setup right, then the fixed points that you can't generate with the group action product theorem, they come from this bilinear map. Okay, so I think I'll stop here. Okay.
Thanks very much, Brendan. So if we can all unmute and give Brendan a round of applause for a very nice talk. So now it'd be great if anyone's got any questions for Brendan, if they can either put them in the chat or unmute or raise their hand.
I have a question.
Mm-hmm.
So in what ways, this is an evil question, so I apologize.
Yeah.
So in what ways are you sensitive to the rank of GLN? Where does that show up? I'm sure it shows up everywhere, but
yeah, the dependence on the rank is bad. I think like you'll get some implicit constants that are like n to the n or something like that. Yeah, so this in the 3x3 case, you only have to use this bilinear map once, but actually in the n by n case, you might use it, I guess, up to n times. And you'll get sort of n different images, and then you have to multiply all of those together. So it's very dependent on the rank, with not very nice dependence.
any further questions?
I have a slightly unfair question because I think I know the answer. So actually, yes. Am I allowed to say this? So Brendan very nicely sent me a copy of his paper a few days ago, and he said there was something he could not quite do, namely that to ensure that a stronger version of the conjecture is true. So he was, namely, what would be the stronger version? Namely, that S is normal in the group generated by A. Is there any chance that you would be able to prove that as well, or not?
I'm not sure. It doesn't fall out naturally, and I tried, I didn't get it. So the very general Briard-Green-Tao theorem, the qualitative one, doesn't get that S is normal.
Yeah.
So I'm not sure. I guess it may or may not be true, but it doesn't seem to fall out of this proof.
It's beautiful, by the way.
I really like it. I mean, if we proved it for FP, it's because we didn't know how to prove it for FQ. It's very easy to get stuck. So it seems that you have got a really clean solution.
Yeah. So actually, you can just ignore all this bilinear form stuff too over FP, so it gets a little bit nicer there.
Well, but no, but
well, not ignore
the linear form stuff. Yes.
Yeah, but
yeah. I mean, that's what allows you to solve the problem. Yes.
Yeah.
So are there any further questions? Could I
Sorry,
go
I
ahead.
had another question.
Yeah, go for it.
Harold's question made me think of this. So at what point in your argument do you actually pick out S? When does S appear?
So I actually split things into two arguments. So there's so you have these homomorphisms that come from ratios of elements on the diagonal, and so you sort of want to distinguish between when those ratios are like always equal to 1 and when they're not, but you actually want a gap. So you either want that the number of ratios is quite large or it's 1. And so you can kind of prove under the assumption that that the number of ratios for all the non-trivial characters is large, then you can prove a result. And then basically you just, to prove without that assumption, you just pigeonhole and you say, if I have, so many terms with too few ratios, then I pigeonhole and I get rid of them, and then I check to see if I've now all the ratios are good, and so you do this maybe up to n squared times, and then once you've made sure that all these ratios are large, that's where S comes from, and the cosets that you've thrown away come from sort of these few ratios that are left over. Yeah, so in the paper, I guess it's sort of split into these two steps, and it's pretty easy to pick out where S comes from. And that's kind of where you'd hope to maybe prove that S is a normal subgroup, but it seems like sort of certainly the kernel of these bad ratios, that's a normal subgroup, but then you pass to a subgroup of that, and then you don't really retain control there. But yeah, it's pretty easy to split out. It's the noise comes from these like sort of poor ratios.
Well, to avoid going over 1 hour, I think we should call it a day there. But if anyone does have any further questions, I do have one quick question. I'll stop recording and feel free to stay behind and ask questions to Brendan if you've got time, Brendan. But before we do that, if we can all thank Brendan again for a very nice talk.
Thanks.
So our next speaker next week is Georgios Petridis, and he's going to be speaking at the time of 7 p.m. British Summer Time.
Okay.
I hope to see some of you next week.
Cool.
Okay.
All right. Thanks.
Cheers.
How do we subscribe? Because I got the link from a friend.
Oh, you shouldn't be in here, Harold.
Oh, sorry.
It's okay. I can put the link in the chat. There's a sign up form on a website, and I'll
Excellent.
send you that now.
Thank you.